Chapter 6 is titled Systems of Linear Inequalities. Let's review. The language of inequalities. If I have an equal sign, that's read as equal to or is. X is equal to 4 or X is 4. If I have a greater than, that's X is greater than 4 or X is more than 4. If I have a less than sign, that can be read as X is less than 4 or X is fewer than 4. If I have a greater than or equal to, that can be read as X is greater than or equal to 4 or X is at least 4. And if I have an X is less than or equal to, I can read that as X is less than or equal to or X is at most 4. Operations of inequalities. When we're dealing with inequalities, we treat the algebra the same, except for division and multiplication of negative numbers. If we need to isolate x in this example, where negative 2x is greater than 4, when we divide by negative 2 on both sides, we have to switch that inequality to get x is less than negative 2. More review. How can we graph a line if you're given an equation? My equation here is negative 2x plus 5y is equal to 10. Step 1. Find the y-intercept. The y-intercept of a graph is where x is equal to 0. So for example, here is the y-intercept on this line. To find the y-intercept, set x to be 0 in our equation. So negative 2x plus 5y is equal to 10. Negative 2 times 0 plus 5y is equal to 10. Divide by 5 on both sides to get y is equal to 2. Since points are written as x comma y, 0 comma 2 is the y-intercept. Our x value is 0 and y is 2. Step 2 is to find the x-intercept. These are the two easiest points to find, the x-intercept and the y-intercept, because one of the variables is always equal to 0. So the x-intercept is where the value of y is equal to 0. So y is 0, here's our x-intercept for this line. To find the value of the x-intercept, set y to be 0. Negative 2x plus 5 times 0 is equal to 10. Negative 2x is equal to 10. So our x-intercept is at the point negative 5, comma 0. Step 3 is to plot and join the points on graph paper. So here are my 2 points. I have negative 5, comma 0, and I have 0, comma 2. These are my 2 points for my line, and then I join them with a ruler. When you are graphing inequalities, there are criteria for colors that you have to follow in this textbook. So if the solution contains equality, so if it's equal to, greater than or equal to, or less than or equal to, and is continuous, use a solid green line for the boundary to show that all points on the boundary are included. If the set contains equality and the solution set is discrete, for example integers, stipple the boundary with green points. If the linear inequality excludes the possibility of equality, so if it's just greater than or less than, draw a dashed line to show that the points on the boundary are not included. Use green for continuous, orange for discrete. Use green shading for continuous solution sets and use orange shading with green stippling for discrete solution sets. For example, here we have points x and y such that y is less than or equal to negative 2x plus 5. X is in the rational numbers, y is in the rational numbers. So that means that no matter what, there will always be a number between two numbers. So between 2 and 3 is 2.5, between 2.5 and 2 is 2.125, etc. So I color this green, and I have equality, so I use a solid green line. These can be found in your textbook as well. Here I have the points x and y such that y is greater than, notice there's no equal to here, negative 2x plus 5, where x is in the rational numbers and y is in the rational numbers. So here, because I don't have equality, I use a dashed line, but it's still continuous because I have rational numbers, so it's going to be green. This third example, I have x and y such that y is greater than or equal to negative 2x plus 5. Here, x and y are both in the integers. That means that 1.5, 2.5, anything with decimals are not going to be included in the solution set, so I have to use stippling. It's going to be orange, but it's going to be green. Dots. Here I have x and y such that y is less than negative 2x plus 5. X is in the integers, y is in the integers. Here I use an orange dashed line because I do not have equality. Here's what you will need. You'll need some kind of graphing technology. I use a TI-83, graph paper, ruler, and pencil crayons. We're going to do an example. Graph the solution set for this linear inequality. Negative 2x plus 5y is greater than or equal to 10. Step 1. Using graph paper, graph the line negative 2x plus 5y is equal to 10. The domain and range are the set of all real numbers. This means the set is continuous. There's always going to be a number between any two given numbers. So we're going to use a solid green line. Here we go. Here's my graph. I'm using a solid green line. The set's continuous and involves equality. Next thing, what half plane of the Cartesian plane is going to represent the solution set? Is it going to be the bottom or the top half? So if you look back at this graph, I have point 0, 0. Point 0, 0 is either going to be included in my solution, so my solution could be the bottom half of the Cartesian plane, or it's not going to be included in my solution, in which case I have to color in the top half of the Cartesian plane. So I'm going to test point 0, 0 because it's the easiest one to test. Test 0, 0 in the equation to see if it meets the criteria for inequality. So negative 2 times 0 plus 5 times 0, well, that's 0. Is 0 greater than or equal to the right side, which was 10? Since 0 is not greater than or equal to 10, 0, 0 is not in the solution set. Therefore, our solution has to be above the line. Because the set is continuous, we'll shade it green. So now I go back to my graph, and I shade in the top half of the Cartesian plane green, because 0, 0 is not part of my solution set. To graph negative 2x plus 5y is greater than or equal to 10 on a TI-83, the first thing you have to do is solve for y. Negative 2x plus 5y is greater than 10, greater than or equal to 10, sorry. Let's put that in there, greater than or equal to 10. 5y is greater than or equal to 2x, so I added 2x to both sides. Y is greater than or equal to 2/5 x plus 10 over 5, so I divided by 5. Y is greater than or equal to 2/5 x plus 2. Notice how I did not have to divide by a negative number, so my sign didn't change direction. Step 2. Turn on your calculator and hit y equals, and then we're going to enter this into the TI-83. So I've turned on my calculator and I've hit y equals, and that brings me up to here. Then I've entered 2/5 x plus 2. To find your variable x, you actually can use this button right here for your variable x. Next, I need to determine whether the set is going to be above or below the graph by doing a test. I'm going to test 0, 0. In this case, I've already done that because I've drawn this out by hand, so I know that my solution set is going to be above. So what I have to do next is select the shaded area by moving the cursor left until it reaches the line symbol. So here's my line symbol. So I'm going to move my cursor left, and then I'm going to hit enter until it gives me above. Oh, there we go. I can see that this is going to be above the line. If I wanted below the line, I would just hit enter again, and that gives me below the line. So I'm going to find above again. There we go, that's above. And then I'm going to hit graph. So you can see it will shade my solution area for me. It's going to be above the line. So just notice on a TI-83, I can't change this y equals, I can't change that equal sign to anything else. So I just have to think about it, do a test to figure out whether my shaded area is going to be above or below the line. Alright, let's talk about set notation a little bit. This garble here might be a little bit confusing at first, but I promise it's not that bad once you get used to it. So here I have the set of points x comma y. This straight up and down line means such that. So I have x comma y such that x minus 2y is greater than 1. xei and yei, that means that x is within the set of integers and y is within the set of integers. So I know I'm dealing with integers, so my set is going to be discrete. It's not going to be continuous because 1.5 is not part of the integers, negative 1.5 isn't, but 1, 2, negative 1, and negative 2 are. So it's discrete. Let's graph this on a TI-83. Step 1, I have to solve for y. I subtract x from both sides, and then I need to divide by negative 2. Here I'm dividing by a negative number, so I have to switch this sign. So y is less than negative 1/2 x minus 1/2. So I'm going to graph it on a TI-83 using the steps. Turn my TI-83 on, go to y equals, and then I enter this. So I've entered in my values in the y equals menu. Now I'm going to hit graph. I hit graph. I can see that 0, 0 is going to be above the line in this case. So I need to see what area of my graph is going to be shaded. In order to do that, I'm going to test that point 0, 0. 0 minus 0, well that's equal to 0. So is 0 greater than 1? No. So 0, 0 is not going to be included in my solution set. So I have to shade below. So I'm going to go back to my y equals menu, going to cursor over, so that I get to this line symbol, enter, enter until I get to below, and then I'm going to click graph again. And you can see it shades the area below the graph. Let's do a real-world example now. A store makes $100 on shoes and $120 on boots for every pair sold. The manager wants to make more than $600 per day on these items. What combinations of shoes and boot sales will exceed this daily sales goal? I said, let x be shoes, y be boots. 100x, because it's $100 for every pair of shoes, plus 120y, $120 for every pair of boots, is greater than 600. Since stores cannot sell half of a shoe or boot, or they also can't sell a negative shoe or boot, I know they're going to only sell whole numbers, so my set is going to be discrete. I solve for y. Y is equal to negative 5 over 6x plus 5. And then I can graph it on the TI-83. I plugged in my solving for y values here, and then I hit graph. It gives me this line. Now I need to see whether point 0, 0 is going to be within my solution set to determine if my solution set is above or below the line. So test 0, 0. 0 is greater than 600. Is that true? No, it's not true. So 0, 0 is not included in the solution set. Therefore, the region above the line is the solution set. So if I go back here, cursor over to that line, and hit enter until I get above the line, there we go, and then I hit graph, it will graph the area that is above the line. Possible solutions. If you look here, I'm going to go, okay, 1, 2, 3, 4, 5 over and 3 up. 5, 3 is a solution because it's a whole number. It's a whole number set and it's in the shaded area. 6, 0 is a solution. 4, 3 is a solution. Any whole number pairs in this shaded area will be possible solutions for this problem. And that's it for 6.1.